Okay. So let's begin with our second lecture of this session, of this course. So today, as I discussed in our previous lecture, we will begin with, before we go any further about the quantum mechanics part, which is the technical part of this course. So in our first lecture, we have done the formulation of the Schrodinger equation. Okay. So how that equation is kind of derived, you can say, okay, from the fundamental principles over here. And then we went on to understand that time dependence usually, we ignore in almost kind of all the practical circumstances, because time dependence influences only the phase part, okay, not the amplitude. And the amplitude is more important for us, for our main concern, because our amplitude will give us something which is kind of the intensity of the wave, or in other words, the probability of finding that particle within a particular region of the space. Okay, so we derive this time independent form of Schrodinger equation, which will be our mainstay as far as all the quantum mechanics and solid state is concerned. Okay, now if we have principles of the forces, their particles, and their fields, if we have time, if time permits, we will essentially go to our next topic of fundamentals of quantum mechanics, which will be useful to us. As I mentioned in our previous lecture, quantum mechanics is a huge subject. It's like an ocean. However, we will concentrate only specifically those aspects of mechanics which is the bare minimum requirement for our understanding of the devices. Okay, so we will look into quantum mechanics as nothing more than a mathematical tool for understanding the device modeling, PMMD, physics and modeling of microelectronic devices. Okay, so for that we will require to understand the probability current density, which we will do it if time permits. So before we go into that, this is what our topic, this will be for today: the fundamental forces in nature and their elementary particles which are involved in those fundamental forces, as well as the fields concerning it. Okay, so, and in the process we will understand the concept of particle spins. Is that fine? All right, so these are certain illustrations which I have drawn over here. You will understand the significance of it. This we have done, I have drawn over here to give you certain examples of the different spins. Okay, we say that electron has half spin, spin half, and all that, right? So we will try to understand that. So let's begin with the class. So here we have got the nature of the physical models or the theories. Okay, so let us first understand this, like let us first appreciate the nature of the physical theories. So and in this today we are not going to go into mathematics unless we go into the quantum mechanics part, but I want you to appreciate certain concepts as a scientist. Okay, today we are scientists, not engineers. Okay, so as a scientist, first realize that any scientific theory, okay, begins as a hypothesis. One person somewhere in the world, okay, he will essentially come up with some concept that, okay, this might happen this way. Typical example, Planck's hypothesis. Okay, E is equal to h nu. Now, later on, it comes into the second phase called theory, when he is able to develop a mathematical model for it. Okay, and that model, that theory, that mathematical model can essentially help to understand related phenomenon. Okay, for example, Planck's hypothesis E equal to h nu. Okay, let me just write here as an illustration. Okay, here let us say E equal to h nu. Now this fundamental principle of like E equal to h nu, the quantization of energy, this was essentially started as a hypothesis. Okay, later on this was applied in let us say photoelectric effect. Okay, this was done by Albert Einstein, and essentially we have something in that photoelectric equation. Einstein used this concept. In fact, it was used in other like black body radiation as well. So in all those experiments, like in all those phenomenon, this was used, and later on it turned into sort of a theory, because this mathematical model was being used to predict new phenomenon. Okay. So only when the model is applicable to other phenomena. From there, so it after it came over here, it became a theory. From the photoelectric effect, later on, this was experimentally proven. So that only then it becomes a law. Okay, this is the nature of any theory. For example, you come across, you do some mathematics, that essentially is a hypothesis. If that mathematics essentially gives you a model like this, then that using that model you can predict new phenomenon in nature. You can predict, okay, I have developed a physical theory, let us say a hypothesis, and then that is in, let us talk about electromagnetics. Okay, so in electromagnetics also we had a set of hypotheses which turned into Maxwell's laws. Okay, only when it was experimentally proven by Faraday. Okay, so this is how mathematical models or physical theories evolve. Now, whenever we say we have essentially got a physical law, okay, then also there are cases then what we find is that, okay, this physical law, now let us take a typical example, Newton's laws of motion, for example, okay, or Newton's law of gravity. Let us say talk about gravity here. Okay, now Newton's law of gravity was good enough for explaining all the phenomena which we see around us. Okay, now note, this is very important. For the phenomenon we see around us or we perceive around us, this is kind of a pretty important thing to understand. I will explain it in a more details later on. Now this Newton's law of gravity, okay, and similar certain laws, they basically constituted something called the classical physics. Okay, okay, now this classical physics, if you think about it, Newton did not sort of invent classical physics. Newton developed the models, as I said. Newton developed the models and essentially turned all the earlier physics into the models which we have today. So Newton was instrumental. Newton was a great scientist, and essentially he made physics into the mathematical description that we know today. For example, he understood that, okay, if a car accelerates, then you cannot use the algebra. You cannot use algebra to define it. That's why he came up with a mathematical formulation that is called calculus. All of you are aware of this, right? So he, along with Leibniz was in Germany, if I'm not wrong. So Leibniz and Newton, they essentially came up with a branch of mathematics which can define or which can explain classical physical models. Okay, so this calculus as a part of yeah, please. Hello, excuse me. Please switch off your microphone. Yeah. Unless you have to speak to me. Okay, so you're having calculus over here. So Newton and Leibniz, they essentially came up with this mathematical branch. Why is it necessary? Okay, just to develop the mathematical models to explain classical physics. So basically, Newton's calculus essentially helped to convert hypothesis into the classical theory. Is that part clear? Now, with experiments and all, it turned Newton's laws. That's fine. Now, later on, what happened is towards the middle of the 19th century, so let us say 1850 to say 1900, within these 50 years, there had been several inventions, several experiments, which proved that there are certain flaws in this law of gravity. So, for example, Newton's law of gravity could not explain the slightest variations of some experimental observation in Mercury's trajectory. Okay, Mercury, you know, is a planet, the first planet in the solar system. First, with respect to the distance from the sun. So Mercury's trajectory, or let us say Mercury's orbit. Okay. So Mercury's orbit around the sun, there was a very small variation with the accurate observation. So it took us a lot of time. Let us say Newton was in 1600, I think. So uh, what happened is before Newton also classical physics existed. Okay. So what Newton did is that he gave a mathematical description or the model for the classical physics which we had and turned them into the classical physics as we know it today. Okay. Mechanics, as we say, Newtonian mechanics or classical mechanics is what he developed. Now that was unable to explain the if you observe uh, Mercury's orbit accurately. Now, okay, so if you want to observe something accurately, you need the proper experimental setup for that. You need proper like Hubble Space Telescope for that, isn't it? So it will take some time. That also requires some like improvement or advancement of the technology and all that. So during Newton's time, we cannot say that Newton developed a very no, not at all. What Newton did was, according to the available knowledge at Newton's time, he did excellent. Okay, so now we know better, and as a consequence of that, scientists started thinking that okay, Newton's law of gravity need to be modified. Note, we cannot claim that Newton's laws are all rubbish. No, not at all. But Newton's laws are correct within a particular um, range of observables. Okay, so if you want to analyze the trajectory of let us say an apple falling from the tree, Newton's laws are perfectly fine. But if you want to think about much larger perspectives like Mercury's orbit, okay, whenever you are trying to use Newton's laws for galactic motions, comets and all that, then probably Newton's laws need some modification. That is where we get Einstein's laws and all that. Okay, this is how scientific theory advances. Okay, so in fact, I'm not going into the details about it. You must have studied. All of you must be knowing like how classical physics converted into the quantum physics and all that. Now, based on certain experiments, okay, like let us say wave particle experiment, okay, Arthur Holly Compton's experiment, that is Compton wavelength experiment. Okay, so there are several experiments. Photoelectric effect is another experiment. So that basically came up. People started thinking, okay, there is a wave nature of particles, there is a particle nature of waves and all that. Now, what I want to bring into your perspective is that all this wave nature and all that began with 1900. Okay, so now you will start appreciating what I'm trying to drive at. 1900 onwards, okay, all the technology which you see around us have been developed within the last 100 or 150 years. Let us be safe because now it is 2020. So let us, within the last 150 years, all the technology, all the physics that we know it today is not old at all. Whatever we know, 99.99% of the theory, what we know today, whether it is technology or science, has been invented within the last 150 years. Whatever we knew earlier was essentially kind of, I mean, for example, quantum mechanics. The whole world is driven by quantum mechanics today. We will see in a few minutes now. That was invented after 1900. Relativity, like whatever I told you about here, like the issues with classical physics was kind of resolved by Einstein's laws. It was 1900. After 1900. Okay, so now let us dive into a little bit of the nature of physical models, the fundamental forces and elementary particles. Okay, so where was I? Yeah. The first concept of gravity, the first force over here, the first fundamental force we will discuss about is gravity. So you must have heard about Aristotle, right? He is a Greek scientist, philosopher, whatever. Now, what Aristotle thought, that the first concept of force essentially came from Aristotle, but he did not develop any model or a theory, which Newton did it. Okay, so what Aristotle thought is that there are only two fundamental forces in the universe. One is called gravity. Okay, what is the other force? Levity. Okay, what is gravity? Gravity means essentially gravity is the force or the tendency that certain particles will always sink. It will always fall down. Levity is the property that the particles or that matter will essentially go up. As simple as that. Remember, this is Aristotle. Aristotle was during the time of Alexander, I think, like Greek, I mean, during the golden age of Greeks. Okay, so gravity, this is, now you will find it, you will see this. But at one point of time, I'll tell you, this was the theory which was prevalent all over the world. Okay. So as I told you, whatever knowledge we have is only after 1900. Okay. So before that, they are all nonsense, bullshit. Anyway, let us think about some bullshit here. What, like thousands of years ago, people used to think. So there are only two forces, fundamental forces, gravity and levity. Gravity, we have got two kinds of particles. I mean, according to Aristotle, one is called earth element and the other one water element. He used to call them as element. Remember, this element has got nothing to do with the elements and compounds in case of chemistry. The word chemistry was not invented during this Aristotle's time. Now we have got levity is another force, which essentially, as I told you, the tendency of certain elements to rise up. The first one will be air element, and the other one is the fire element. In fact, this was so popular. If we look into our Sanskrit Vedic literature also, you will find this same kind of concept: earth, water, fire, and air. Okay, so it is the property of fire and air element to rise up. It is the property of earth and water element to sink or fall down. Okay, now during that period of time, during that era, people suddenly observed that the force of gravity and levity, how is it happening? They did not understand the idea of the force. That is where I will come into. Now, at that time, what they thought is that these forces will also require an element on its own, because it turns out that what is this earth element? It's basically anything solid. Anything solid is earth element. What is water? Any liquid, simple. Okay. What is air? Anything gaseous. Fire is fire, as you know. All right. So it turns out that if you're having an earth element, let us say a piece of rock, that is also earth for them. Okay. So if you have a solid element and you essentially put it in water, it will still sink because of gravity. If you just if you just leave a stone, it will again fall on the ground within air. So what they realized, means the Greek scientists during that time, is that irrespective of the whether that solid or the earth element is within air element or water element, it always sinks. So it essentially means that the force of gravity and levity will require some element on its own. That's why they came up. They simply, as I told you, that these are all hypotheses. There is no mathematical basis for all this. There is no mathematical model for this theory. For this hypothesis, I'm sorry, it's not a theory. You cannot call it as a theory unless you have a mathematical model. Now you try to connect the dots. You know something about devices, right? Many of you are from electrical background. You have just thought about some formula based knowledge and all that. So unless and until you actually develop a model for the devices, you do not know much about it. Okay, it's like a story. For example, right now I'm telling you a story. There's no mathematics over here. Aristotle told a story. Okay, so just because the earth element will sink in water or air, so they thought that gravity or levity, this is a property. These forces can act in a separate element, which is called ether. Now, please remember, this ether has got nothing to do with the element which we know in organic chemistry. Okay, the ether which we know in organic chemistry was invented much later, so we are not going into that as of now. So in fact, that was also a misnomer. They thought that ether element, the chemists who developed that thought that this is only the ether which we have been looking for in Aristotle's time. No, that's not that. So this term ether, what is this element? So 1, 2, 3, 4, 5. So the fifth element is ether. Now this fifth element ether is something which you cannot perceive. However, it is ubiquitous. That means it is present everywhere in the universe, and it is through ether that you have all these forces. Okay. So this was the first concept of the particles and the forces in nature, which all of you might be smiling right now. This is all nonsense. Okay. Now, what is amazing is that even Isaac Newton, okay, even Isaac Newton, when he wrote the Principia Mathematica with the Newton's laws of gravity, he thought that this Newton's law of gravity is valid only under this ether. This concept of ether was ruling the roost all over the world until Albert Einstein came up. And through his theory of relativity, he said that the gravity that we know it today is basically the warping of space-time coordinates. I'm not going into relativity right now. It is too much at this stage. So now, it was Professor Albert Einstein who essentially came up with a mathematical model of the universe. That is why it's called Einstein's laws, which essentially explained that this concept of ether is nonsense. It's not necessary to have any force. And what he explained is that force or the transmission of the force of any kind does not require any medium at all. So that means this concept of ether is totally bullshit. Got it, everybody? Okay. So in Hindu philosophy, if any one of you are interested, you will know that in Vedic literature also we have got this earth, water, air, fire, and ether. This ether is nonsense. In fact, I'm a follower of Swami Vivekananda. So Swamiji, when he addressed so many people, in many of his lectures you will find he has mentioned about ether. Okay. So as a student of science, when I first read it during my BTech and all that, during that time, so when I went through, I mean Swamiji's lectures and all that, I was feeling really very I was feeling bad that why did Swami Vivekananda speak about ether which doesn't even exist. Please note that Swami Vivekananda died in 1902. In his lectures in Chicago, which he made a history about, that was given in 1896. Okay. Einstein's laws were published in 1905. Okay. So in 1905, when Albert Einstein refuted the idea, he mathematically proved that concept of ether is nonsense. Force does not require any material medium at all. Swamiji had left us. Okay. So that means what I'm trying to prove it, I don't want to digress. I'm just giving you a valid proof that every knowledgeable person before 1900, okay, they believed in this ether concept. They believed in gravity, levity, all these things. Okay, everybody. So try to realize that whatever science and technology, whatever we see around us was invented only within the last 150 years. Okay. So now we will come to the modern world. Okay. But this, I started with this little bit of history. You can kind of get things in perspective. There had been thousands and thousands of years of evolution of human knowledge. They were all nonsense. Only within the last 100 and 150 years, we learned something which is really worth it. Now, this was, and by the way, remember that the all the physics which we had before 1900 was practically only gravity. People knew only one aspect, that is gravity and levity. Okay. Now, let us come to the next topic. Is that what is the current view of the world? Now, in the current view, in the present day, I am not going into the details about how things evolved from Aristotle all the way to Stephen Hawking. I am not going into all the historical annotations. Now I'll directly fast forward to the current view of the world. Now, in nature, we have the forces, and later on, the scientists came up that all the forces are essentially because of certain elementary particles. Okay. Now, what's known earlier than that was that every force will have some region of space around it where the influence of the force can be perceived. Okay. For example, in your higher secondary, in your +2, you must have done the experiments, right? You have a magnet somewhere. Okay. You have a magnet here. Then you will find there are the lines of force. Okay. You must have done this experiment in your school. I'm pretty sure you must have done it. Okay. Then you'll have to find out the arrows. Fine. So then you will have to say, okay, North Pole, South Pole, and all that. So what you will observe is that these lines of force are essentially that will be available only within a certain region of space or certain region of volume around that particular magnet. So what we understand is that every force will have a certain range within which its its influence can be perceived. You can essentially perceive, you can feel its existence. Correct? This is called the field. And the distance from the origin of the pole to this is often called the range of the force, or the field is the region around it. Okay. And these are the flux lines or the force lines. We will see, we will understand that later. Now, so this is the concept of the force and the field which you know. Now, in the modern physics, okay, after 1900, people started understanding that there are only two kinds of particles in this whole universe. ठीक है? सिर्फ दो ही किस्म के particles होते हैं. ठीक है? Now, one of the particles will be having integral spins. Okay, so only two particles are there. One will have integral spins, particles with integral spins, and the other one will be particles with half integral spins. Now, these are all topics of statistical mechanics, which we will slightly go into dealing with the quantum mechanics part in this course itself. We will go slightly, means we will derive certain equations, and we will try to understand those models much more details. Okay. Now, these integral spins are the particles which constitute matter. Integral spins are the particles which produce force. Okay. Half integral spin particles produce matter. That means throughout this whole universe, not just in atoms. Everything in the universe, whatever you see, whenever you see solid matter, solid state, not just solid, liquid matter, matter in itself, atoms and molecules, they are composed of half integral spin particles. Okay. Whereas any force which you see, they are also produced by particles. However, they are having integral spins. Okay. Now, let us understand the meaning of the spins over here. So, if you are having, this is the concept of the particle spins. So, integral spins समझना थोड़ा आसान है. So, integral spins mean the particles which will be having either zero spin like this, or it will have okay, let me write this. They will either have a zero spin, or they will have one or two. Okay. Now notice that if you are having, excuse me, if you are having a zero spin, that means irrespective of the rotation of the particle, whatever spin it will always be symmetric. Typical example of spin zero particle are phonons. Okay, we will come into phonons in much more details later on in the course. Now, that is so phonon, as I told you, this other, if it is an integral spin, either 0, 1 and 2, that means these particles constitute what? The forces in nature. Okay? So phonon, as I told you, phonon is an example of an energy particle. That means it will be having integral spins only, 0, 1, 2. And those phonons are essentially responsible for vibrational energy. So that means you simply heat a material. Okay? So that means you take silicon, or simply let us say your laptops have already heated up because of the listening to me for the last half an hour. What will happen? Your laptop is heating up, right? Your smartphone is heating up. Why is that happening? Phonons are created inside the solid state, okay, inside the silicon. That heating up of your laptop or your smartphone is essentially because of your IC getting heated up. And IC comprises of silicon, and the silicon heats up in the solid state because of the phonons generated. So that means it is generating spin zero particle inside the material. Okay? So spin zero, you can clearly understand, no matter how much I rotate, it will always be symmetric. It is a perfect sphere. It's a ball. It's a football. It's a baseball, cricket ball. Okay. Now let us come to the idea about spin one particle. Most of the forces which we see around us, they will essentially comprise of spin one particle. We will see the examples after some time. Now, in spin one particles, like photon, electromagnetic radiation, that is a spin one. Now, if it is a spin one particle, what do we mean by that? Okay, here if you notice, okay, this is a typical spin one particle. An example of spin one is that you need to have one revolution to make sure that you get the same so that you can have the same observation. Okay, so let me rotate this. Okay, you see the spade was only up, right? So essentially you'll have to turn 360 degree like this, and only then it will essentially become the same. Understood? Huh? So this is, that means, so it is actually annotated with the revolution symbol below the ace of spades card, that you have to rotate entire 360 degree to make it one. So that means it will require one revolution to make sure that it reaches back to its original position. Understood? So that's why it is called spin one particle. This is the example of a spin one particle. Of course, this is the card. This is just an illustration that the original spin one particle, which is a photon, have to be rotated like 360 degrees so that you can have the same observation. Okay. Now, this is an example of spin two particle. Let us do the same over here. If you notice, I am rotating this. If you rotate just once, you reach out to the same thing. Okay, it's like symmetric. So that means half the cycle. So that means rotating 180 degrees is sufficient to get the same observations. That is a typical spin 2 particle. Okay, so we will understand that, as I told you, example, the phonon vibrational energy particle is an example of spin 0 particle. Okay, so you can also ask me why phonon is this. Photon, the electromagnetic radiation, the tube light in your house, let us say, the light which is coming from your laptop or your smartphone screen, that is photon. Photon is a spin 1 particle. Okay, you require like this. Example of spin 2 particle is graviton. Okay, so graviton is the particle which produces gravitational energy, gravitational force. We will come into that after some time, after we understand the spins. Now, so spin 0, 1 and 2, they are essentially defining the energy particles which we will encounter. So graviton, the force particle which gives you gravitation, is the spin 2 example. Okay, spin 1, electromagnetic radiation, microwave radiation, okay, is photon, LED, laser. These are all spin 1 particle. Spin 0 particle is the reason why your laptop is getting heated up. Phonon is an example. Now, the most important particle which we will encounter in our electronics as a circuit designer, okay, as a circuit designer, as a device designer, as an engineer, is electron, isn't it? Now, remember, in your school days, you did not study about phonon. So let me just write here, just as an example. So this is an example of phonon. This is an example of photon. This is an example of graviton. Of course, there are other particles which I am not going into the details. I mean, I learned all that in CERN labs, so I can go on and on. But let's just you know all these forces like gravitation. You are all aware of. Gravitation is the reason that you are sitting down nicely in your couch. Okay, photon is the reason why you are able to see light. Phonon is the reason why your smartphone. Okay. Now, these are the forces which we encounter. Now, the spin half particle, typical example is electron. Now, in your like +2 in your high school, you have studied, right, that atoms are essentially made of electrons, protons, isn't it? So spin half particles are electrons, protons, and all that. Notice that electron, proton, these are matter particles. As I told you, matter particles are having spin half. Okay. So now, by the way, when I was working the Higgs boson experiment in Switzerland, I was working with bosons, right? So bosons are essentially, again, energy particles. Here it will belong into the spin 1, spin 2, spin 0, this category. I don't want to go into the physics of Higgs boson here. Okay, so now we will understand spin half particle. Yes, spin half, these are very complicated looking structures, right? So let us understand that through a GIF. Now notice that if this is our original structure, now these green, blue, and red, they represent the various lines of force. Okay, in fact, this can be said as the Lorentz force, if you remember. Okay, in case you remember, just I'm trying to give you a physical feel of this. One is the magnetic field, electric field, and the motion or the force. Okay, so these are the like 3 directions of the lines of force. Now, if you notice that in all these cases, the spin of a particle is defined by the number of rotations required to bring it to its original state. Okay, na? So in spin 0, no matter what you do, you will always remain in the same state. In spin 1, you require one complete rotation. In spin 2, you require two. You can basically rotate it just half the cycle. So that means within a full rotation, you will get two spins of the particle. Okay. Half spin kya hai? The particle will return into its original state with respect to all the lines of force, electric field, magnetic field, and the force lines. Only if you rotate it twice into the 360 degrees. So that means it will require a 720 degrees rotation. Let us understand this from here. So just keep in mind that we will take into account the red, which is in the axis. The green should be here, going up on this side and going down on the other. So now let us understand it from the GIF. Okay. So if we begin with this particular understanding, look, the red is here. It will move. The green is turning on this. So after the full 360 degree rotation along the on this plane, the green was inverted. Now the green is back again. Notice this. Green is over here. Just observe where I'm keeping my mouse. This is my hand. Look, now the green is going upwards. We needed the green to come on the down, right? Again, observe this. So let us say over here. Notice where I'm keeping the mouse. This here was the green color. After one 360 degree rotation, green has come on the other side. There is no green. Another 360 degree rotation. Notice. Now the green is coming back. So again, observe this. The blue was here. Look at the mouse position. Now, look. After 360 degree rotation, the blue is not here anymore. Another 360 degree rotation along the horizontal plane. Now the blue appears on this side. Okay. So it requires how many? Notice 1. This is one full rotation, 360 degrees. And this is a second rotation in the 360 degrees. Now it is essentially in the same orientation. So it requires two 360 degree rotations to bring it into the original configuration. Understand? Everybody understanding with me? Okay. Notice the green has shifted over here. Even though the particle has been rotated 360 degree, and it's not okay. In the second rotation only, you will be getting the green on the same place where we had earlier. Okay, everybody please respond if you are able to understand. Please visualize this. Hello? You won't find it in the textbooks and all. Okay, so you require, for the half spin particles, you require the particle to rotate 720 degrees to essentially come back to its original configuration. All right, so
Excuse me, sir.
yes.
Sir, what line of force does the red line represent? Because it needs only 360 degree rotation.
Yeah, so what I am suggesting is that the red line is, it's basically, I'll tell you, this is just a GIF I found on the internet. Okay, but I had to explain you why the particles are having a spin of half. So spin 0, spin 1, you can understand, it's kind of easy. All electron, proton, you will all throughout our course we will be telling, because of spin half we will have to put 2, multiply all the density of states by 2 and all that. So why does that happen? Because of this factor. What these lines of force are, we don't know. This is just an illustration of solid geometry. Okay, so this is just geometry. All I'm trying to tell you is that what is the concept of spin half? In reality, what happens is an electron, when it is inside an atom or a solid state material, it will be subject to Lorentz force. So there are 3 forces in a charged particle. Okay, one is the magnetic force, magnetic lines of force, that is represented by capital B. I can draw it here. Yeah. So all I'm saying is that if you have a particle here, then Okay. Okay. So the right hand screw rule, you might remember. So what will happen is one of them will be the B, okay, other one will be V, other one will be F. Okay. So the Lorentz force F will be equal to V cross B. So if that is so, in that case, this will be different. This will be velocity, this will be V. Okay. So these forces which we are trying to tell you is a Lorentz force. Now this Lorentz force is essentially it will be kind of influencing all the charged particles inside the matter. Okay, and all of them are mutually perpendicular to each other. So if you notice here, the green is over here, blue is on this side, this is, so these are essentially like a Cartesian coordinate system. Now it is getting like deflected, that is a different issue. But if you look at this, let us say that the electron, these are all mutually perpendicular, orthogonal. Okay, so this is an illustration to explain what is the meaning of spin half. It simply
Excuse
means,
me, sir.
yes,
Sir, the spin half particle is electron. When
yes,
electron is so small, how will we come to know that after two spins, I mean after two revolution, it will be in the same orientation?
yeah.
It
No,
is
that
so
is
small.
possible. No, it's not. For example, electron is so small, nobody has seen electron in their eyes in the whole world. But you will always get to know about it from the experiments where you are essentially talking about the ensemble of the electrons. Okay, your IC fabrication course has started, right? ICFT.
Yes, sir.
ICFT. In your ICFT, Parikshit sir will teach you. Probably there is a lab component also, if it is possible, um, about the Hall experiment. Okay, so over there you will. How do you observe the kind of the doping of the material and all that in Hall effect? It's a matter of the ensemble of millions of electrons which we are working together. So that means if you want to try to know the spin of a particle, it is quite possible in high energy physics. In ISC Bangalore, when I did my PhD over there, there was a complete department of high energy physics. So over there, they are essentially doing the elementary particle studies and okay, it is possible to find out the spins. But as you might be thinking that how to find out the spin of a single electron? No, not necessary. Why would you require? For example, when you are having a current, do you bother about the amount of charge being flowing for a single electron? No. If it is like 25 ampere current, 25 ampere current is sufficient to drive an electric train. Local, okay, so local trains in Bombay carrying probably lakhs of people. Okay, those electromotive like uh, EMU trains, it is called. Okay, so those EMU trains, electric trains, electric local trains, they are essentially running with the help of electrons. So does it mean that you need to know what is the charge of an electron? Not necessary. So similarly, the spin of the electron can also be determined as a final observation based on millions of electrons. Trillions of electrons will produce 25 ampere current. That is good enough. Okay. All right.
Yes.
So where was I? Okay. So now we have understood the spin half particle. Now let us conclude today's class with the fundamental forces which we said. Now the gravitational force, once we have got the very basic idea about the integral spin particles, which are the force particles, and the half integral spin particles, which are the matter particles, let us understand the fundamental forces of nature and their field ranges. So the first force that was discovered in science was essentially the gravitational force. Okay. Now, the only reason why we can even understand the gravitational force, we realize that gravitational force exists, is because of its range. As I said, field or range. Okay, by the way, do you have a class after this? Hello?
Yes, sir. Yes, sir.
So,
Yes.
which class do you have after this?
RC.
Arts.
Uh,
Okay,
yes.
reconfigurable computing, fine. So now, if you're having a gravitational force, which was the first force invented, so you will notice only reason why we realize this gravitational force is because of the field or the range it applies to. So the range or the field of the force is essentially extends to light years. That is the reason why when we are looking into the skies, when we are looking into the galaxies and all that, those galaxies and the space and all that, solar systems, they are all defined in like light years and all that. So over there, the only force that is prevalent is the gravitational force. Okay. Now the gravitational force will act on matter particles. Now the property of the matter particles which it acts upon is the mass. Okay. Now the matter particles, as I said, they will always have spin half. Correct. So all matter particles have spin half. Now, but matter particles will have different properties. For example, electrons, they are charged particles, all right, but they still have some mass. Okay. So mass is the fundamental property. So the property of the particles which gravitational force acts upon is the mass. Okay. So, but they will be, all these mass particles are essentially having spin half. Fine. Now, in terms of the strength, the gravitational force is the weakest among all the four fundamental forces. Now, then in that case, you might ask that why is, if that is so weak, how we are essentially able to find that all the largest like celestial bodies, like let us say the sun and the moon and the earth and the Jupiter and all that, how are they being governed by gravitation? It is because that its nature is always attractive. So if there are, let us say, 10 to the power of 10, like let us, how much shall I write? If there are 10 to the power of 1000 particles, which is a, you can understand, it's a huge number. Now all this 10 to the power of 1000 gravitons, okay, each of these matter particles, 10 to the power of 1000 particles, they are essentially emitting graviton with spin 2. What will happen? But they are all attractive. That is the reason why, even though the graviton is the weakest among all the force particles, still it is going to have an enormous amount of gravitational force. And that is the reason why all the celestial bodies are, you know how it is, like Earth is rotating around the sun because of graviton. Okay. Because why is it? Because the mass is larger. So that means if a body has got a huge mass, then basically graviton, it will essentially play its role. And again, it is something very interesting to note that graviton is the massless particle. So that means if the force particle graviton is massless, practically massless means its weight is so low. That is the reason why it can traverse through light years. Okay. For example, its mass is so low. That is the reason why the gravitons which are emitted by the Earth and the gravitons which are emitted by the sun, they can essentially travel through space for millions of kilometers. Okay. Now they are able to move. Now you might be thinking, okay, but still graviton is massless. Okay, they are moving, but they are also the weakest. Then how come graviton is essentially kind of make sure that even Pluto is revolving around the sun? The reason is, I told you, it's the mass which matters, because gravitational attraction, the gravitons, they are always attractive. Okay, so there is no positive, negative, and only attract, and the positive will repulse. They will be repulsive. No, no, no. Gravitons are always attractive. As a consequence, if there is more mass, gravitational force will be more attractive. Okay, so the properties are massless and they are uncharged. Now, as I put Aristotle over here because he had absolutely no idea about gravitons and all that. However, the gravity, I mean, as I told you, gravity concept was kind of available in gravity and levity was there in Aristotle's writings. The theory of gravity was essentially developed by Newton, then later on improved upon by Albert Einstein, and the current theory which we know for the black holes. And of course, black hole was invented by Fred Hoyle, but that is different. But Stephen Hawking is essentially a kind of, he was there for the string theory and all that. So the modern perspective of the universe is essentially, let us say, about the Hawking's theory. So this is what gravitational force is. All right. Now, second in line to gravitational force was the electromagnetic force. Okay. Notice the range of this electromagnetic force or the field is in the micrometer. Okay. Think about this. This is light years. This is micrometer. Since it is so small, what will happen? You will observe its influence only within microscopic domain. Okay? So that is the reason why if you want to have a device, you cannot make a device with 1 meter. Okay, you have to make the device at least in micrometer scale. Okay, so now if you are essentially making an electromagnetic force of this order, beyond this order, you will not feel any influence of the existence of this electromagnetic force. Okay, what are the various particles we see? These are all spin half particles, electron, proton, quark, and all that. Okay, now these are all subatomic particles. Okay, now what is the strength of the particle? Notice this is where it becomes really interesting. It is 10 to the power of 42 times stronger than gravity. Now, the electromagnetic force, later on we will, we will not have time for that. In the next class, we will begin with electromagnetic force and the rest. So what we'll observe is that the electromagnetic force is 10 to the power of 42 times stronger than gravity. Okay, that means if the electromagnetic force is there in the atom, okay, atomic structure, you remember nucleus is positively charged, electrons revolving around it, Rutherford's and Bohr's model. Okay, now those in that particular domain, which is in the scale of nanometers, in that nanometer domain, okay, electromagnetic force is very, very strong. And in that domain, in the solid state material itself, gravity has got no power at all. That is the reason why if you have a solid state material, let us say your, remember in the last class I told you about the ceiling? Inside the ceiling, it is solid state material. So inside the solid state, there are atoms are there, right? Now those atoms are held together by electromagnetic force. Now these electromagnetic force are 10 to the power of 42 times stronger than gravity. So even though the entire ceiling is is like, let us say 2 tons, one of you wrote 2 to 3 tons, which is a good estimate. So if it is in the order of several tons above your head, but it doesn't fall off because the weight of 2 tons is supported by a weight 10 to the power of 42 times of that. So that means if the weight force, the force which is pulling your ceiling down is 2 tons, the force which is keeping it stable is how much? 2 into 10 to the power of 42 tons. Understood? So answer the concept which I wanted to put in your heads in the last lecture is that why is it that the ceiling, even though it is weighing tons, it doesn't fall off over your head? Because the force, the electromagnetic force, the weak nuclear force, all this quantum theory will essentially define that the forces at the atomic realm, the solid state material, the mortar, the infrastructure, those let us say, what is there? Metal sheets are there, right? So the metal sheets inside that mortar, inside that ceiling of yours is essentially having 2 into 42 times stronger, 2 into 42 times stronger. Okay, so that's the reason why your ceiling doesn't fall off. Okay, it's 11 o'clock. I think you have got another class. In the next class, we will start going through it from here. Okay. In the next class, we will finish this off and then we'll begin with quantum mechanics once again. Thank you so much. So the answer to this is whenever as we are going along this direction, we are essentially going from smaller and smaller range. It was in light years, gravitation. Here it is 10 power minus 6 micrometer. Weak nuclear force, the radioactivity force, is essentially in 10 power minus 9 nanometers. Strong nuclear force, that is the within the nucleus, that is 10 power minus 15 or femtometers. So the range decreases. As the range decreases, the strength increases. Okay, so now when there is an earthquake, small breakage happens over here. Then what will happen? This 2 into 10 to the power of 42 tons is lost. Then gravity. So that is the reason why even the slightest break, slightest crack in a flyover can bring the entire flyover down. The slightest crack in the World Trade Center can bring it down, because you are essentially breaking this 10 to the power of 42 times stronger force, which is keeping it together. Okay, and in the next class we will understand how much breaking should it happen so that it can break down. Okay, this is where I stop today. Thank you so much for joining.